Understanding slope and knowing how to calculate the slope of a line is one of the most important building blocks to creating the equation for any linear relation. Remember that in math, we use the lowercase letter m to represent slope. The equation of a line has a template, which we can also refer to as slope Y-intercept form. And this template is the equation y equals mx plus b. We know about 3 of these variables already. The letters x and y together represent a coordinate point found on the line, and we know that every coordinate point has an x value and a corresponding y value. The letter m represents slope, or it could also represent rate of change. Remember that slope and rate of change are essentially the same thing, except for the fact that slope is typically just represented as a numerical value, and rate of change is represented as a numerical value with units. So the only thing that's really new at this point is this letter b. And the letter b represents something that we call the initial value. And another term that you might come across either in this video or in upcoming videos is that b can also be referred to as the y-intercept. A y-intercept is where your line in question will intersect or cross or touch the y-axis. So your line will always touch or cross the y-axis at a particular point or a particular value, and that value can be referred to as the y-intercept, or it could also be referred to as the initial value. So as we saw in a previous video, there are numerous different ways that you can calculate slope or rate of change. Today, we are going to focus specifically on the b value, or the initial value. And why that's important is because depending on what that b value is, it is going to indicate for us if we can classify our line as either being a direct variation or having a direct variation, or having what's called a partial variation. This video specifically is only going to focus on a direct variation, so this is kind of part 1 of the topic or the lesson, and we'll focus on partial variation in a second video, which I will follow up right after this video. A direct variation is a relationship between 2 variables in which one variable is a constant multiple of the other. So what that means is that your data points are increasing or decreasing by the same consistent value. That's going to create a linear relation or data points that graph as a perfectly straight line. What's very specific, though, about the graph of a direct variation is that it is a straight line that passes through the origin. And if you remember from our previous lessons on scatter plots, the origin is a very particular coordinate point or ordered pair located at 0, 0. So any line that is considered to be a direct variation, it will always start at the origin. So its starting value will always be 0, 0. So if our graph starts at the origin, we then can say that we know that the initial value of our graph is also going to be 0. And remember, we use the lowercase letter b to represent initial value. So in a direct variation, then we can say that b is equal to 0. If we know that b is equal to 0, we can take that information and input it into the template for our equation of the line. So I rewrote the template for the equation on the screen, y equals mx plus b. The only thing now is that I know what my b value or initial value is. I know that it is 0. So I can actually input that into my template. But to say mx plus 0 is kind of pointless because that's like saying mx plus nothing. So if I were then to simplify this template or this equation a little bit further, that would then leave me with y equals mx. So y equals mx is the base template for any linear relation that you are classifying to be a direct variation. The b value or the initial value is 0, which is why we don't see anything attached here at the end of our equation. So a direct variation will have some value of slope, according to how steep that line is. And of course, it will have multiple different x and y values along its line. Therefore, we can use this equation, y equals mx, as a shortcut to rearranging and isolating the slope of that particular line. So if I take this equation y equals mx and I rearrange it to isolate for m, that would leave me with this, m equals y divided by x. So this is another variation of how I can calculate the slope of my line that happens to be a direct variation. So let's put this all together with an actual example and calculation. So in the first example, the Frederick family travels 250 kilometers to a relative's home. The distance, represented by lowercase d and measured in kilometers, varies directly with the time, represented by lowercase t, which is measured in hours. So this question is a good question because it's telling you explicitly in the wording of the question that it varies directly, which is another way of saying that this is a direct variation. So knowing that it is a direct variation, we know that one of the data points on our line is going to be 0, 0. This line is going to start at the point 0, 0. So the first part asks us to determine the slope of the line relating d and t, distance and time, if the distance is equal to 43 when the time is equal to 0.5. So if the distance traveled is 43 kilometers, the time then will be half an hour. So we need to calculate the slope, and once we find it, we just have to interpret or explain what this rate of change value represents. Remember, slope and rate of change are the same thing. We're using the word rate of change here because we are looking at information or data that has units. Distance is measured in kilometers, time is measured in hours. So there's lots of different ways that we can find slope, but remember, because they've told us that this is a direct variation, we know that we can find slope by taking our y value and dividing it by our x value. So then the next thing that you need to think about is which variable goes where. Will distance be found on the x-axis or the y-axis? Will time be found on the x-axis or the y-axis? So you kind of have to think about which variable is going to be the independent variable and which one is going to be dependent. And they've kind of made it nice and easy for us because they've included one of the variables as being time. And we know from past lessons and past videos that time is always an independent variable. It is always plotted on the x-axis. So this 0.5 hours is an x value. And if time is our x value, then by process of elimination, distance has to be a y value. It has to be a dependent variable. The distance that you travel depends on the amount of time that you have spent in the car, driving in the car. So knowing this now, we can just take those values and plug them straight away into our slope equation. So if I input my values, in the place of y, I'm going to put my distance value that they gave us in the question, which was the 43. So I'm going to write 43, and I'm going to include the units, which are going to be kilometers. All of that will be divided by our x value, which is our time value, and our time value was 0.5, and that was measured in hours. So now we can go ahead and calculate our slope, which should work out to be about 8.6. So that is our slope value. But then if we put in the units attached to the 8.6, which are kilometers per hour, that turns it into a rate of change. So what does this really represent? Well, it tells us that the Frederick family can travel 8.6 kilometers every hour. All right, now that we have that information, they want us to determine how long it will take the Fredericks to reach their destination. Now, their destination is going to a relative's house, and that relative happens to live 250 kilometers away. So that is the total distance that they need to travel, according to the question, to get to this relative's house. So to determine the amount of time it's going to take them to travel 250 kilometers, we're going to first need to start with an actual equation. And then we can plug all the information into that equation to calculate the amount of time. So we're going to start by using our equation template. Remember, because we know that this is a direct variation, we know that our equation template is going to take on the form y equals mx. Remember, there is no initial value on the outside of that equation because direct variation means that our initial value is going to be 0, and we don't need to include that 0 in the equation. All right. Normally, we could just go ahead and plug some numbers in and do that calculation, but we do need to be very specific here, and that is because this question gave you particular variables to use in order to represent distance and time. Remember, variables are always plotted on the x and y axis, so we're going to have to take those letters d and t and insert them into the correct spots. So we said that distance would be plotted on the y-axis, and we used distance as a y variable. So we're going to replace y with the letter d. Then we have our equal sign. We're still keeping the letter m for slope. Remember, m is always used to represent slope. And instead of the letter x, we will input the letter t because time is always plotted on the x-axis. So now we can go ahead and plug in our values. So we know that the distance traveled by the Frederick family is 250 kilometers. So we can plug that in the place of d. M represents slope or rate of change, and we calculated that value in part A, and we determined the rate of change to be 8.6 kilometers per hour. So we can plug in 8.6 in the place of M. And we don't know what time is. That's what we need to solve for. We need to solve or determine how long it's going to take them to travel 250 kilometers when the car can only go 8.6 kilometers every hour. So to isolate for t, we need to use opposite operations. We can see here that 8.6 is being multiplied by time. So the opposite of multiplication would be division. So we need to divide both sides by 8.6. Okay, on the right-hand side, we know that 8.6 divided by 8.6 is just going to give us 1, so that's going to disappear or cancel out. We don't have to write the 1 in math, so on the right-hand side, we can simply just write t. On the left-hand side, we are going to do 250 divided by 8.6. When we divide, it doesn't give us an exact whole number, but if we were to round to the nearest whole number, we would get roughly about 29. So we can write a concluding sentence and say, therefore, it would take the Frederick family 29 hours to reach their destination. Let's try another example. About 1/3 of all water used in homes is for toilet flushes. The table below shows water use for a standard toilet manufactured after the year 1985. So they've given us some data in a table of values. So we have a column where they're telling us the number of flushes and they are counting upwards by 5s. And then we have a second column for water usage that is measured in units of liters. And so we can see the corresponding volume of water that is used for each number of flushes. So for 5 flushes, that toilet would use about 65 liters of water. So the first thing that we need to do is to graph the data. So to graph the data, we need to figure out which of these two variables presented in the table of values is going to be the independent variable. And remember, the independent variable is plotted on the x-axis, and which variable will go on the dependent axis or the y-axis. So I know that if I flush the toilet, well, then I flush the toilet. That's great. But the amount of water that my toilet is going to use up is dependent on the number of times that I actually flush the toilet. So if I don't flush the toilet, then I'm not going to use up any water. But if I flush the toilet 5 times, well, then the toilet is going to need or use 65 liters of water. So the number of flushes is the independent variable, and that is going to be plotted along the x-axis. And water usage in liters is the dependent variable, and that will be plotted along the y-axis. So for the number of flushes, because I can see very clearly in the table of values that the data is skip counting or increasing by 5s, I'm obviously going to make my scale count by 5s. With the water usage, however, it might be a little bit more tricky to figure out what an appropriate scale would be. I can see my smallest value is 65, but my highest value is 390. I need to be able to fit all of these values along the y-axis. It's got to fit onto this grid. So I think I'm going to skip count by 50s, and I should be able to fit in all of these numbers onto this grid. So I went ahead and plotted my graph, and you can see it on the screen. Just a couple of things to take note of. Don't forget to put on these little arrowheads at the ends of each of your axes. I plotted all of my data points on the grid, and I found that they were pretty linear, and they were able to connect together with a smooth, straight line. I also make sure that I labeled my axes. So again, on the x-axis, I have number of flushes, and on the y-axis, I have water use. And if they include units or provide you with units in your table of values, you need to make sure that you're including those units in your label as well. And I also included a title. Typically, when we are titling our graphs, the template that you should try to follow is you take whatever is on your independent axis, you write out the word versus, so not the abbreviated VS for versus, but you actually write out the word versus, and then you write in your dependent variable. So for us, I have a title that is number of flushes versus water use. Question B then asks us, is this a direct variation situation? And we need to explain how we know. So again, recall that a direct variation means that your graph is starting at the point 0, 0. So if we think about this logically, we know that if we don't flush the toilet, so that would be an amount of 0 flushes. If I don't flush the toilet, I'm not going to use any water, or the toilet is not going to use any water. So 0, 0 is actually a valid data point for this scenario. So you can see here on my graph that I plotted the point 0, 0, and I just kind of extended out my line this way. It kind of didn't come out smoothly, but I can connect this line to 0, 0. And same thing goes if I took a ruler and put it flat onto my grid and extended out my line, I can see that because this is a nice linear relation, the line actually does extend down and will go through the point 0, 0 quite accurately. But in terms of actual consistent data points, 0, 0 would logically make sense for this scenario. So I went ahead and filled that in, and I stated, yes, this is a direct variation since the graph goes through the point 0, 0. The next part asks us to determine the rate of change, and then they want to know, what does this value represent? So remember that rate of change is just the same thing as slope, but your answer will have some units attached to it. And remember, there is a lot of different ways that you can calculate the slope for a linear relation. You could choose to use your graph. You can pick 2 points, draw a triangle between them, and then determine rise and run. Or you could pick 2 numbers from your table of values, and you can go ahead and use the actual slope formula or slope equation, y2 minus y1 over x2 minus x1. So I went ahead and chose 2 random data points from the table of values. I picked 565 and 20, 260. And the first thing I'm going to do is I'm going to label my points x1, y1, x2, y2, and I'm going to transfer those data points into the slope formula. When you're transferring your data points into the slope equation, don't forget to include units because units were given to you in the original question and with the original data. So my y2 value is 260, and 260 was a volume, so I'm going to put in the units of liters, minus my y1 value, which is 65 liters. All of that is over my x2, which is 20. Now, 20 doesn't really have any units. 20 is representative of the number of flushes. So there are no units, but if you really wanted to, you could write out the word flush. So I'm going to say 20 flushes minus my x1 value, which is 5. And that again is 5 flushes. So if I go ahead and do the math, 260 minus 65 is 195 liters. And 20 flushes minus 5 flushes is 15 flushes. And if I divide 195 divided by 15, that works out to 13 liters per flush. So our rate of change is 13 liters per flush, and that is really what that value represents. It means that every flush of the toilet uses 13 liters of water. So one single flush uses 13 liters of water. The next thing we need to do is we need to write the equation or come up with an equation to represent water use with respect to flushes. So because this is a direct variation, remember we know the template for our equation has to take on the form y equals mx. They didn't pick any specific letters for us to use to represent the number of flushes or the water usage. So we're just going to stick with the same letters that they've given us in the template, which are y and x. If they had given us particular letters to use, we would have to make sure that we switch them out for y and x in the correct spots. So the only thing then that we really need to do is just input our value for m. M is the slope or the rate of change. So we calculated the rate of change in the previous question, so I'm just going to input that or insert that into the equation. So my equation then would be y equals 13x. And so now that I have the equation, I can go ahead and calculate how much water is used for 17 flushes. So I know that 17 flushes represents my x-axis. Flushes was plotted along the x-axis. So I'm going to insert or substitute 17 in the place of x. So I'm going to rewrite my equation, y equals 13x. And in the place of 13, I'm going to substitute 17 for 17 flushes. And then I'm going to go ahead and calculate that. So that's 13 multiplied by 17, which is 221. So therefore, 221 liters of water is used for 17 flushes. So to summarize, the main thing to remember for a direct variation is that it is a linear relation that goes through the point 0, 0. So if you're looking at a table of values and you want to tell or predict whether or not it's going to be a direct variation, you should be looking for the data point 0, 0 to appear in your table of values. If you are looking at it from a graph, your graph should start at the point 0, 0, which is also called the origin. And if you're looking at it in terms of an equation, remember that direct variation linear relations take on the form of y equals mx. So your equations could look something like y equals 2x, you could have y equals a quarter x, or remember the letters x and y could be switched out to use very specific variables depending on the scenario or context of the question. So maybe you might see something along the lines of d equals 5t.